just move on appending have a different point. Make sure you get the board right. Okay. We ready? All right. See you later. Maybe there's some lights in the back. You want to try these lights over there, or maybe they're next to the door. There gotta be some lights in the back. Yeah. So what are we? Orders of growth. Let's recap a little bit those three functions. The big O, theta, and omega, and then we'll talk about two more. We have a homework, right? Which is due when? Wednesday. This Wednesday? Today is Wednesday, right? Tuesday, sorry. A long holiday, I lost track of time. So when is the homework due? This is very easy, so it should really be due before, but everybody starts, some of you are new here, so we give it more time. But this homework should not take more than, I don't know, 2 days, something like that. So what did we say about big O? Let me try to make some sort of nine table here. Big O. That is, say F is O of G. That means F is upper bounded. By G. Informally, we say F is smaller or equal than G. That's not a mathematical thing. It's just we can say that F is at most G, right? And the definition of it is there is some sort of constant. I don't know if I called it C or D last time. You guys can tell me that. F of n is smaller than, I think I use C or D? D times G of n. So there is a constant D, which is positive, and there is an n0, that's a start. And for any, an n0 here, and for any n starting at n0, we have this relation. So again, the idea here is that while the beginning n smaller than n0 might do anything, we don't have any constraints for the beginning, starting at some point, this relation happens. Okay? So that's that. Let me give here some example. I could have f equal n or 2n and g equal 1/2 n. The relationship will be correct because 2n is O of 1/2 n. There is a constant to make this work. Right. In fact, any two linear functions will be in that relation. I have to say f is 2n and g is 0.01 and log n. Then 2n is O of 0.01 and log n. Okay, so that's one thing. Next one, if f is lower bounded. normally we say it's at least G. We should say F grows. F grows at least G. And here we have a constant positive and a starting point. And for every n starting at the starting point, F is at least that. So that is F is here. Omega to this big omega. Here we have functions like, of course, they could be both linear, 2n and g, just like before. This would work. 2n is omega of 1/2 n. Or f could be strictly bigger. Maybe f is n squared log n, and g is, g of n is, say, n log n. Then we have n squared log n is omega of n log n. Obviously, this is a bigger function. Then, if both of them happen, then we say f is like or similar with g. The notation is f is theta of g, or g is theta of f, because they're the same. And here we have both constants, c smaller than d, a starting point, and starting at the starting point, f of n is between d, g of n, and between c times g of n. And we say f is like g, or f grows like g. Now, of course, we can have any linear functions just like before. Two linear functions would fit into the theta of each other. In fact, any two polynomials, if f is a degree 3 polynomial, n squared minus, so say n cubed minus 2n plus 5, and g is another degree 3 polynomial, 100 n cubed plus 3n squared plus 10n plus 2. Those functions are both degree 3 polynomials, right? Is it true that this n cubed minus 2n plus 5 is theta of 100 n cubed plus 3n squared plus 10n plus 2? Are in the theta relations of each other. Can I find two constants such that this is bigger than constant c times this, and it's smaller than constant d times that? At some point. It doesn't have to happen for n equal 1, 2, 3, 4. Maybe it starts at n equal 100 or 1,000 or 1,000,000. That's okay. I can choose the starting point. What will be the constants? What will be the c and d? So what I want here, I'm going to erase this. You can leave it because it's correct. But I'm going to say what I want here is n3 minus 2n plus 5 to be smaller than some d times 100 n cubed plus 3n squared plus 10n plus 2, and to be bigger than a c times 100 n cubed plus 3n squared plus 10n plus 2. Right? That's what I want. At starting some point. So what would be the c and d? Can you give me a c that would work? What c do I need here? to make this work. You can pick the C. The story with those constants is that you can pick any constants you want as long as you don't change them. Once you pick them, once you put a value in one of them, you cannot change it. That's why it's a constant. So this n, what's the coefficient to this n squared here? 1. What's the coefficient this n squared? 100. I have to get rid of this 100. So that could be 1 over 100. But then I still have to make calculations. Since I can pick the C, I can pick something even smaller than 1 over 100 to make my life really easy. For example, 1 over 200. If I pick 1 over 200, now the coefficient of this n cube is 1/2. This coefficient is still 1. This will eventually beat that, right? I don't have to worry about the lower terms. If I pick 1 over 100, n cube is the same like n cube. Because this is coefficient 1, now this becomes 1, right? Can you guys follow me here? If I do 1 over 100. The problem is that minus 2n is not going to overcome the 3n squared, so on and so forth. This is going to be a bigger term. Well, it's divided by 100, but still it's an n squared versus an n. If I play with the main coefficient to get 1 over 200, I don't have to worry about the other terms. Now I have a 1 versus 1/2. That's going to be dominant, right? You may need to play a little bit arithmetics and L'Hopital rule if you're not convinced. But since I have the freedom to choose any C I want, I choose one that satisfies the relation from the dominant coefficient, right? How about the D? I have 100 n cubes here versus 1 n cube. I can pick an easy D here, D equal 1. And then I have 100 n cubes. I don't have to worry too much. This is going to be a lot bigger than the n cube. But to be perfectly rigorous, so like in a math class, you would actually have to prove the n0. So to be perfectly rigorous, I need an n0 when this starts happening. This may sound trivial, and it is simple, but in practice, it's going to require some calculations. In this class, you don't have to always point the n0 and always make all the calculations. In a formal class, in a math class, you'd have to do that. In here, you just have to prove somehow, make an argument that n0 exists. So how do we say, okay, what's a reasonable n0? If we pick this coefficient, this C and D, right? So in here, look at this. This thing in here, 100 n cubed plus 3n squared plus 10n plus 2 will be bigger than this quite from the beginning. I think I can start at n equals 1. Yes. And so from here, n0 is 1. I can pick 2 n0s and then took the, if I get an n0 for which it starts working here and 1 n0 for which starts working here, maximum. My overall n0 or final n0 will be maximum. Right? So what? Now the problem in here, how do I get this to work? This is, what's this left side? This is 1 over 2 n cubed, right? Plus 3 over 200 n squared plus 10n, no, 1 over 20 n plus 1 over 100, right? This has to be smaller than, I'm going to say here, want. When I put a sign like want or a question mark on it, it means I don't know that to be true, that I want it to be true. When I don't put a 1 means I already know it's true, I've proven it already. But if I put a 1, it means I have a desire out of a sudden, right? This is n cubed minus 2n plus 5. So now what? Move the terms around, right? So let's move everybody on the right side, say. So I get 0 smaller than 1/2 n cubed minus 3 to the 200 n squared. How about n's? This is minus 2n, this is minus 120. So the total number of n's is what? 2 plus 120.
Minus 21, right?
That is, this is 41 maybe? Yeah. Over 20. And Now 5 minus 1 over 100, it's 499 by 100, something like that. Because I have 500 over 100 minus 1 over 100, it's 499 over 100. So I need this to be bigger than 0. Now, see, in this class, you could stop here and say this polynomial goes to infinity, right? Because the dominant coefficient is positive, right? We assume we know that. Any polynomial that starts with the main coefficient being positive eventually will reach infinity. Eventually, will not just reach infinity, will be monotonically increasing. Polynomials can do a little bit of waving around the roots, right? They're not monotonically increasing, right? You remember parabolas or some other functions that go up and down? But eventually, at some point, they just start increasing and they stop. So we assume we know that. You could prove it if you want, but I could just say there is at some point, like graphically here, the polynomial might do whatever, but at some point it just starts increasing, right? And when it does that, I say that's my n0. From now on, this is going to be bigger than 0. So I could try to find an actual n0 here. I bet if I start with n equal, for example, 10, I bet that this thing starting at n equal 10 will always be positive, because 10 to the cube is how much? 1,000 by half? 500. This 10 square is 100. Divided by 100, it's about 1. This is like 3 by 2. It's a small constant. 10 by 20 is a 2. That's about 20, and so on and so forth. I think this 500 here will dominate the rest of the thing. So if I really have to pick an n0 explicitly, I'm going to start at n. I'm going to guess here n0 equal 10. Now, maybe you can make a better guess than me, a smaller, but remember, it doesn't matter if it's 10 or 20. You're not better if you pick a smaller n0, you know? Unless the problem specifically asks what's the first n for which this becomes available, then you really have to calculate that n. But even this would be not necessary in this course if you have an equation like a polynomial, because for polynomials, you know there is an n0 for which they start to be monotonically increasing. Now, there's a problem if this coefficient is negative. If this would be a negative coefficient, that would never work, because negative coefficients will make the polynomials go down, not up. Okay? I still need a proof in a math class that starting at n0 equal 10, that would work. We don't need it in here for this function. If you have to make such a proof, how would you prove it? If somebody asks you to say, starting at n0 equal 10, prove that this thing is always positive. How can you do that? Induction's one way. Another way is to argue that if it's positive, I can plug in n0 equal 10, get the value, right? The value, say, is 345. If I can argue that all the roots of the polynomial are on the left side, means once it's positive, there's no roots on the right side. It doesn't touch the axis anymore, right? So sometimes you see this argument at n0 equal 10, it's positive because I can put the value in. And no root higher than 10 can happen, which means it cannot go lower than 0. Therefore, after n0 equal 10, it's always positive. Induction is another way. And there are other decomposing. You know, you can decompose the polynomial into smaller factors if you know how to do that. There's ways to argue this thing. Okay? So the story of theta is that the functions grow together. Let me put another example here for theta. How about f is n log n and g is 1 over 1,000 n squared? What's the relationship between those two? I want to say f is what of g? Isn't it theta? So it's certainly big O, because this function would be smaller than this function. How do I know? I ignore the coefficients on all these kind of functions where it's a coefficient times something. I ignore the coefficient. It's not that easy when there's two coefficients. For example, 1 over 1000 n plus 50 square root of n. Now it's two coefficients. You can't just say ignore the coefficient. But when there is only one coefficient, here's a constant times some function, you can from the beginning ignore the coefficient. 1 over 1000 doesn't matter. It's just the n squared that dictates the growth. Same thing in here. Whatever coefficient I have in front of the function, doesn't matter. It's just the n log n. So how do I think in terms of n log n versus n squared? I can divide with an n to start with, and I'm left with log n versus n. Right? So in here, I'll have to say n log n is smaller than some constant d times 1 over 1000 n squared. That's equivalent to say log n is smaller than some constant d. I'm going to ignore the 1 over 1000 because I can include 1000 into d. D times n, which is equivalent to say log n over n is smaller than a constant. Now, why is log n over n smaller than a constant? We assume we know, I assume you guys know how to deal with this thing. I assume you know how to prove that log n, any logarithmic function in n, it's going to be eventually smaller than any polynomial function in n. But why is that? Like if somebody asks you, prove it, what do you do? So logarithm of something, any argument, n to n, 3n, n squared, it's smaller than that something. Right? So logarithm, why is it that logarithm of any expression, I'm going to say here's the function, whatever function is, it's smaller than the function itself. Right? That could be n squared, n cubed. In this case, it's n, and n, right? Or if I have to prove this, we don't have to prove it. We assume we know it, but you know, to make assumptions like that, we know it. You actually have to know it. Okay? Logarithms are smaller than polynomials. So any logarithms of n is smaller than any polynomial of n. Right? So why is that? So here I'm going to give you a hint, and you guys have to go home and make sure you can make this proof. It's easy. The hint is to change the variable. To say, since I have to prove it for every n, or at n starting at n0, all those proofs start at some point. I don't like this variable n. I want to change it to something that's easier for me. Since it's all the numbers, I can write in a different form. What form would I like? E to the n, or 2 to the n, assuming this is log base 2. I think this is easier to say if n is e to the n, or 2 to the n, then maybe transformation. In calculus, this is it's called how? In calculus, when we make this kind of thing, how do we call it? Change of? That's in logarithms, change of base. Change of variable. I don't remember from calculus. Right? Then I get what? How much is log, assuming this is log, natural log, how much is log of n? Now it's n is e to the n. That's n divided by e to the n, smaller than d. How do I prove this? I have to find an n0 and prove it. How do I do that? By induction. There is a small problem, which is what is e? I know you know it's a base of the natural logarithm, but to make any sort of proofs about exponential function, if you go way into mathematics, which we don't want to go, but if we were to go into mathematics, what is e? Right, it's a value, but what's the definition of it? I mean, eventually when you do pure mathematics based on axioms and based on all the proofs that you need, like, you know, formal mathematics, nothing is assumed, proves everything. What is E? Somebody, yes?
The definition is 1 plus 1 upon n raised to 1 by n.
1 plus 1 over n?
Raised to 1 by n. Raised to 1 by n.
But then n tends to infinity.
Like this?
1 by n.
Well, I think you say one this way, right?
something like this, and limit n tends to infinity.
Infinity.
Right. I think it's the limit goes to infinity is the other way.
Yeah.
Is this. So the limit when n goes to infinity of this thing, it's a number. And that number is called e, which is the base of natural logarithm. Now, you should have seen this proof at some point in high school, that if you really have to compute this thing, there's a limit, and that limit is e. This proof is hard. Like, I bet if I ask you right now to do this proof, you cannot do it. This is not an easy proof. But as computer scientists, you should at least know that that's the limit, and this is a sequence that it's convergent to some number e, which is about, how much we said? 2.71, something like that? Okay. In fact, there is, I'm making a small parenthesis here. There is an inequality that you have to know that's fundamental to all exponential functions, but also to calculus and harmonic series. And while proof, again, it's hard, even for college, even for master students, that proof is hard. You know, if you feel you're good at math, take it home and see how you make it a proof out of it. The inequality that you need to know, I think, I have to remember it. I think it's 1 plus 1 over n at n, this one, smaller than, in the other side, I think I have here 1 over n at n plus 1, something like that. And I have to figure out what's in the middle. I have to check a little bit some paper because I don't remember it. In the middle, it's maybe the logarithm. Logarithm of something. So that's e. We get rid of this. Logarithm of 1 plus 1 over n. Not sure. Let me check this out really quick to give you a correct formula. I don't want to lie to you guys. By the way, a lot of this stuff is in a course that I teach for okay, so 2 inequalities that we're going to need. You write it properly. One is 1 plus 1 over n at n is smaller than 1 plus 1 over n plus 1 at n plus 1. That's smaller than 1 plus 1 over n plus 1 at n plus 2. That's smaller than 1 over n plus 1. That's 1. Okay. So I think in this one here is one thing. It's obvious. There's 3 inequalities, right? This one here, it's obvious. The middle one.
Yes.
right? Because this is some base, some number. That's the same base. It's more than 1. And this is a higher exponent, right? So whatever base at power, whatever, 25 will be smaller than the same base at power 26. Because the base is bigger than 1, right? So that's obvious. This in here says that the series, if I compute the series, the sequence, 1 plus 1 over n at n, it tells you what? That if we move to the next term, this is the a n plus 1, right? It's the same form just for n plus 1. This tells you, this inequality tells you that this series is what? Monotonically increasing. This is increasing. This here tells you that if I take a different series, which is very similar to that one, is 1 plus 1 over n, but at power n plus 1. Right? So it's the same base. Note that this series changed both the base and the exponent. When I move to the next one, the base goes a little bit down, but the exponent goes a little bit up, right? This one says that if you are to go from this to the next guy, right? This is the same. This is bn. This is bn plus 1, right? It tells you what? This series is decreasing. They are very similar to each other, those two series. But one is increasing, the other one is decreasing. They both converge to the same thing, which is E. One from the bottom, this one goes up, this one goes down. E is in the middle here, in between them. Right? So this is an increasing series, goes up. This is a decreasing series, goes down, and E is somewhere in between them. Now, try to prove this. Go home and see if you can prove this. Note that this inequality here is stated without calculus and without any reference to the exponential numbers. I can state this inequality without saying what is an exponential. Because I can, since those are natural numbers, the exponents, I don't need the exponential function. I could just say multiply this base by so many times with itself, right? I only need multiplications. If you put a power that's 2.75, you need to define what an exponential function is. How do you raise something at the power 2.75? But since my exponents here are natural numbers, right? 0, 1, 2, 3, 4, 5, I can make the definition of what it is to raise this or that by multiplying with itself 6 times or 5 times. How much is n plus 1, right? So this can be defined in terms of the 5th grade. You don't know what the exponential is. You don't know what the logarithm is. You don't know what calculus is. Here's a simple thing, right? It's hard to prove. Fair warning, this might take you the whole weekend and still not be done with it. But this is a very powerful inequality. Once you have this, you effectively define the exponential base E. Is the limit, this increasing, that decreasing. And you should be able from here to prove this very easily. Now that we have an exponential base E, that's the limit of those two things. 1 over n plus 1 is smaller than the natural logarithm that's in base E of this, smaller than 1 over n. This follows immediately from this inequality. So that should take you not more than half an hour to get from here to here. But this is hard. Once you have this is a very powerful inequality. This defines all kinds of approximations, calculus, integration, also the harmonic series. Later on we're going to see that if you sum up those parts, remember how the harmonic series, it's approximatively the logarithm? How many people remember that? That 1 plus 1 over 2 plus 1 over 3 plus, it's about the logarithm, right? So suppose I want to say the harmonic series of n, it's 1 plus 1 over 2 plus 1 over n. This is approximatively the natural log of n plus some constant. This constant is gamma. So this approximation is very, very, very good. I can get this very easily to follow from the second one. Again, should not take you more than half an hour to do this. The way you do it, you sum up those terms here, that gives you a harmonic series. You sum up those terms here, gives you a harmonic series. But what happens in the middle when you sum up this? This is logarithm of n plus 1 by n. When you sum up those series, log of n plus 1 by n, what happens to that? Log of 3 by 2 or 2 by 1 plus log of 3 by 2 plus log of 4 by 3, right? Because n plus 1 by n all the time. This is called what?
Multiplication.
We know that log of 3 by 2 is log of 3 minus log of 2. So this series will telescope. Remember what telescoping means from high school? No. We back in high school. Okay, let's take these 2-3 minutes to do high school stuff, because high school is important, you know. There's a reason for which we go to high school. That's it. 2 minus log of 1, right? Plus log of 3 minus log of 2 plus log of 4 minus log of 3, so on and so forth. Telescoping means
Log 2 minus log
log 2 goes away with log 2, log 4 goes, log 3 goes away with log 3, log 4, log 4. Eventually, this whole thing is log of n, the last term, minus log of 1, which is 0. Telescoping series are the ones that every term is a difference, some sort of xn plus 1 minus xn. When I sum up all this, they go away except from the first minus the last. That's what happens with those logarithms. So by using this very simple arithmetic here, you could prove from here to here. And this is something most people remember. Harmonic series is about the logarithm, but it's a hard thing to prove. A lot of the ways, you know, try induction straight in here, probably going to fail, right? So that's the natural order. If you do a course in mathematics, when you define the first time the exponential function, you need to prove this inequality, and that's the hard one. Okay? Small parenthesis on logarithm functions. Yes?
Could you just repeat, how do I know that a of n is monotonically increasing and that was...
Well, if you prove this inequality, that's what it tells you. It tells you that an is smaller than an plus 1. This is the next term, right?
Okay.
I'm saying if you prove this inequality, you just prove that this sequence here is monotonically increasing. Same thing here. If this is bn, this is bn plus 1. If I prove this inequality for every n, I've just proved that bn is monotonically decreasing. Once I have that, it's easy to show that those two have the same limit. Okay. And then that limit is called E. One is decreasing, one is increasing. All right. So that's data, and we have two more to add here. There was a parenthesis about logarithm functions. By the way, one more thing about logarithms. All base logarithms are within constants of each other. That's also something you have to know. In other words, you pick any two logarithms, logarithm base 2 of n versus logarithm base not 2, but say 7 of n. There is a constant that I can multiply to make this work. What's that constant?
Log 7. Log 7.
Log 7 to base 7.
You sure?
Yes. Log of 7 to the base 2.
Something like that?
Yeah.
Log of 7 to the base 2, right?
Log 2 base.
Log 7 to the base 2.
Well, try to figure that out. What is it? Right? But what's important for this class, you should know this. What's important for this class is that if I have the same argument, I can change any logarithm into another logarithm by multiplying with a constant. So if the bases are fixed, 2 and 7, there's a constant that multiplies them, and I get it there. So as far as the order of growth goes, all logarithms grow the same, because there's a constant that you can multiply them. That's not true for polynomials, okay, or for exponentials, right? Can I say, can I multiply 3 to the n with some constant that gives me 2 to the n? It's the same principle, right? I want to change the base, but not of a logarithm. I want to change the base of an exponential. Can I say the two exponentials grow the same because there's a constant that multiplies them? No. So it's true for logarithms, All logarithms are in a constant of each other if you change the base, but not true for exponentials or polynomials. Okay. Next up, I'm going to replace big O with small o. So this is f equal O of g. This is small o. You have to be careful when you write this by hand. By computer typing, small o and big O, it's easy to distinguish to each other. But by hand, you may mean small o, and in fact you mean big O. It's hard to read sometimes, the same O, right? O looks the same, big or small. So small o means f is definitely or strictly smaller than G. There is a definition for this, which is f of n is smaller, strictly smaller than d times g of n. That's the same like before. Right? I can put an equal sign. It won't matter the equal sign here in this case. But the meaning is very different than in here. So there is, the meaning there was you can find a constant and a starting point to make it work. The meaning in here is that for any constant, there is a starting point to make it work. So mathematically, this means something very different. Okay? It's not about picking a constant. This is all about finding the right constant. You find the right d, like we did in here, d equal 1, d equal 100, d equal whatever. You find the right and 0, and you show that the thing works. In here, it's not about the constant. This tells you that any constant you pick, it can be extremely close to 0, 0.00001 with 1,000 zeros after decimal. Eventually, G will beat F. A matter the constant. The only constant that will not make it work is 0. But D has to be bigger than 0. Right? So this and 0, of course, will depend on D in this case. Because it has to work for every constant. If you pick a smaller constant, probably you have to choose a larger than 0. But remember that this is not about the constant. This is a behavior that says G eventually beat F within any ratio. So what does this actually mean mathematically? That's a definition, but that's not a good definition. I want you to have a different intuition about this. This means if I take the ratio Fn, f of n, divided by g of n, it's smaller than any constant, right? Any d. At some point. How do I write this mathematically? What needs to happen with this ratio to be smaller than any positive constant?
The limit reaches 0.
It has to converge to 0. So that's the better way to remember this formula. The ratio of those two functions, f is strictly smaller than g, means f by g converges to 0. Because now, if it converges to 0, it means any way I pick a constant, eventually it's going to get low under that constant, right? So, of course, that's easy to prove with some functions. I can take, for example, f equal n squared, and g equal, how about I take n square root of n. By the way, this is how much? This is n at what power?
3 by 2.
3 by 2. And g, say I take n squared, right? How much should be f by g? N by 3, 2 divided by n squared is how much? Minus 1/2. That goes to 0 or not? That's the same as 1 over square root of n?
Yes.
Does it go to 0?
Yes.
So it means f is small o of g. Okay. The last one, may not have space here, but you should try to organize it as a table. The last one is small omega. This has this sign, looks like a W, but it's more curly. So F is omega of G. It means, I'm going to try to write it here. F definitely or strictly bigger than G. F by G should go to where? And I could write that as like in here. In here I would say what? For any constant, there is an n0 such that f of n is bigger than that constant times g. Right? So we talked about this. We say, I want to give you guys a little bit of some things that we don't expect to prove. Logarithm, it's strictly less than polynomials. Strictly less than exponential, which is strictly less than factorial. So I do not need you guys to prove anything logarithmic versus exponential. For example, logarithm of n squared plus 3n is smaller than, say, I don't know, polynomial, 1/2 n minus 5. Less in here, I don't mean mathematically, I mean in that growth sense, right? A polynomial will always be bigger than a logarithm. Right? This would be less than any sort of exponential function if it's in 1.01 at the power n. 0.1, 0.1. Still, this will beat the polynomial, any polynomial. And this will be, of course, more than n factorial. So when you compare things like that, a factorial versus an exponential versus polynomial, you don't have to prove it. But sometimes things could be tricky. What if I have here logarithm of 2 to the n? Well, how much is that? That's n now, right?
Yes.
How about 4 to the n? Log base 2.
To
2n? This is 2n, you said?
2n. 4 to the base 2.
Right? So it looks like a logarithm, but in fact it's a polynomial function. Right? So it's not okay to say this is smaller than 1/2 n minus 5 on the logarithms more than polynomial argument, because this is not a logarithmic function. It looks like a logarithm, but if you open it up in the argument n, it's actually a polynomial. So be sure you don't get tricky. This is a logarithm in n. Even if it's an n squared, it's like logarithm of n. But this is not like logarithm of n. And you can also ask yourselves, what's up to the log of n factorial? This is like what? How does that look like compared to, say, an exponential or a polynomial? Is it bigger than a polynomial? Smaller? Is it like an exponential function?
Definitely smaller than factorial.
Smaller than the factorial because it's a logarithmic. If I am to compare with a factorial, definitely smaller because it comes down to this. It's a log versus the identity function. Identity is a polynomial of degree 1. But what if I am to compare with something smaller, like 2 to the n?
Can I use induction to check?
I'm just saying, you can't say directly, none of these inequalities would immediately tell you what's the relationship between log of n factorial and 2 to the n. Because you can't fit it into polynomial versus logarithm or exponential versus polynomial directly. You have to work it out. How about versus n squared? My belief is that log of n factorial is smaller than 2 to the n. But how about 2n squared?
Yes, it is.
Yeah, it is.
It's smaller than it.
You change
Smaller
the
than n
value.
squared?
Yeah. Just like you said in the second equation, log of n squared plus 3n is smaller than half of n minus 5. Because n
I don't know. Anybody has a computer to compute 10 factorial, log of 10 factorial? Can you try the 10 factorial?
I can do that.
Huh?
Yesterday I did.
I'm not sure. What is the relationship between log of n factorial and n squared of n cubed? Some sort of simple polynomial, that's what I mean.
Yeah.
Is it an obvious relationship? Can we say this is definitely smaller?
No obvious way to say.
No.
I don't think it's obvious at all.
Yes.
I think it's obvious with 2 to the n. That's an easy proof. Log of n factorial will be smaller than 2 to the n, but I don't think it's obvious in here. So try a big value. If I put n equal 10, this be 100, right?
6.55.
This is 6.55, so it's smaller than 100, but I'm not sure it goes like that. It's an exercise. Is it true or not? My point here is that this, if you say this is true because a logarithm is smaller than a polynomial, that's not correct. You have to work it out. This is correct if you have the same argument. This x, 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 x is the same. In that case, you can apply this thing without proof. By the way, n factorial is a very, very prohibitive growing function. If you have any sort of algorithm or memory usage or something that's n factorial, that's not going to fly at all. Quantum computing, you name it, not going to work. N factorial grows. I have a table in the slides here. For even a small n, it's centuries. Okay? So n factorial is very prohibitive. Exponential, they used to be prohibitive 20 years ago, but now we can deal with small exponentials, the basis. When the base is reasonably small, like Fibonacci, it was 1.6, we can deal with that somehow. When the n's are relatively small, the exponents, we can work with exponential that deal with n up to 40 or 50. And quantum computing, which is about to take off as we speak, we are at that point where quantum computing is about to become usable. It was a theory for a long time, but now quantum computing within a year or so might actually solve real world problems. I'm not kidding. Google that, quantum computing. Quantum computing has the promise that can deal with exponentials, which is going to be a breakthrough in computer science, because in computer science we could not deal with exponential algorithms at all. Most of cryptography, for example, is based on exponentially hard algorithms to do stuff. The only way we know how to break cryptography was the exponentially long algorithm. So by making it with big inputs, exponential guarantees that no computer in the world can break cryptography. Quantum computing might break it. Not within a year or two, but eventually. Quantum computer will still not deal with factorials, but might deal with exponentials much better than we deal with them today. Today we're very limited with any exponential sort of algorithm. We can only deal with very small bases or with small exponents. There are some exponential algorithms that we're going to learn in this course towards the end that are still very practical, but they're very rare. Traditionally speaking, excluding quantum computing in this class, exponential would always mean very, very slow. Linear programming, simplex algorithm, is an example of exponentials algorithm that's actually used in practice because in practice it works quite well. Three-sat sort of problems, which you're going to study a lot in theory of computation course, satisfiability of three-sat problems. If you have to solve such a problem, you sooner or later going to have to hit an exponential algorithm, so you have to deal with that. But that's the way assignments for three-sat problems are being computed, with an exponential approximation algorithm. The whole field of approximation algorithms have been invented to deal with exponential problems. Right here. So when we talk about why do we need an approximation algorithm, it's usually because the solution, non-approximative, the exact solution, is exponential. And we will be able to sacrifice a little bit of the solution, the performance, say it's not exact, it's not the best assignment. Knapsack, for example, anybody, right? We heard of that. These kind of things, we don't solve them exact, we don't give the optimal solution, but we obtain a good solution with, say, an approximative algorithm. Also, a lot of graph algorithms are exponential in nature. Hamiltonian paths, for example, optimum Hamiltonian path would be an exponential algorithm. Now, done with this, what we need to move on to is recurrences. So, we're going to talk about recurrences now and next time. That will be on Friday. And if we need to, we may talk about again about it next Tuesday. How many people have seen solving recurrences? Hands up. How do you solve recurrences?
We draw a structure according to that.
Uh-huh. What else? Anybody else? How do you solve recurrences?
Substitution.
How many people have heard of master theorem? Hands up. Okay, very few. How many people can prove or have seen the proof of master theorem? Okay, good. So I don't want to be in high school all the time. I want to make sure that we do some things that are new. First of all, where recurrences show up. So I think we did this last time. So Fibonacci, that's a recurrence. And I'm going to put this example again here, merge sort. I'm sure you know how merge sort works. I have this array, right? Let's throw in some numbers, 8 numbers. 1, 2, 3, 4, 5, 6, 7, 8. So 5, 8, 2, 4, 3, 1, 4, 6, 7. We need a 6, right?
Yeah.
All right. So that's my array. How merge sort works? That's a procedure. It first splits in half. The split actually is conceptual. In an array, the split is just a matter of addressing the array, address the first half of the array. We don't have to do anything. As opposed to say a list or a hash, when you say split, you actually have to produce a new data structure, split into something. In an array, we know the beginning of the array. We know it's a continuous chunk of memory. We know how many bytes, if these are typical integers, takes how many bytes when I say int. So each one of them is 4 bytes. I know how to move so many bytes into the array, so I got the first half, right? So this is conceptual for arrays. For other data structures, I may need to actually do something, but in here, I don't have to do anything. I call merge sort of the array, say that's array A. My notation is I always put the values inside the box, and if I need indices like 1, 2, 3, 4, I put them on top of the box. You don't have to use that notation, but you have to be consistent in how you use it. Okay? So when I write an array, inside the box are always the values. A from 1 to half. In pseudocode, we can write things like that. Of course, that wouldn't go in a programming language. In a programming language, you have to say what the half is. This colon is a notation from MATLAB. Different books or pseudocode use a different notation. It's okay in pseudocode to use whatever notation you are familiar with, if it's consistent. If you decide to use, like me, MATLAB notation, you have to use MATLAB notation everywhere. The colon will be from there to there. But the book might use 2 or 4 or dot dot or arrows. Anything is fine. Right? So I'm going to merge sort these. Merge sort A of half plus 1 to the end. And now I have to merge in the sense of combine the 2. So I'm going to put here another array, let's call it R, equal merge of A. I'm assuming this is sorted now, 1/2. Actually, it's better to write it. Here's I'm computing an array B, an array C, to be more clear, and then I merge B with C into array D, and then I say return D. Of course, when we implement it, we may not need all these auxiliary arrays. Maybe we're smart enough to just do it in place in A if we want to, but conceptually, I'm doing it this way. Now, what's the recurrence that's coming out if I measure the runtime? I'm not worried about the implementation for now. I'm worried how long this is going to take. Remember we did this last time? We talked about how to think of running times. If T of n is the runtime for merge sort of input n, right here I'm making the following assumption, that any array with 100 elements will take the same amount of time. In other words, the runtime depends on the size of the input, but not on the actual values. I'm saying whatever these guys do inside, it won't matter what values are in the array. The only thing that matters is the size. Now that's easy to see for merge sort, but when you start talking about hashes, for example, people say, oh, hash it like a lookup table. Yeah, but then the values you have might actually matter how hashing works. When you do implement a hashing function, for some values it might be easier than for other values. So it's not an obvious thing. In principle, it's true. The time of the algorithm, it depends much more on the input size than on the actual values in the array or whatever data structure I have. But it's not always true. So if T of n is that, what's the recurrence I'm going to have here? For n elements, it's going to take 2 of n by 2 plus T of n by 2 plus how long to do this, merge combine? About n. I'm going to write it now that I know the order notation, theta of n. Or maybe I can just write n for simplicity, assuming I can really do it in n steps. That's another question you could ask. Can I do this exactly in n steps, not in linear steps? Can I do this in precisely n steps? Start with 2 pointers, check, right, which one's smallest, put the smallest in, move on, advance one of the pointer. Will that take n steps? I have to do the check, decide which one to write in the output, and then advance that pointer. That will not take n steps. 2n or 3n steps, right? So it's not n, but it might be maybe 3n. I don't know. Something for you to think about. Linear, I think everybody can agree, that merging, it works in linear time. But if a problem asks what's the exact number of steps, it asks you, is it n or 2n or 2.5n, what is it? So how do I solve this recurrence? We're going to do 3 methods for solving recurrences. And I'm going to show you now one of them, which is kind of the brute force iteration method. The one of the 3, so-called. So what this does, it iterates this recursion until we figure out by pattern, visually, what is it. So here's how that goes. T of n is 2t of n by 2. I'm going to say here plus n for simplicity. It's not n. I know it's not n, but I want to make the math easier. Suppose I have this recurrence. Unfortunately, this is not exactly merge sort, because when I say n, the merge has to work in exactly n steps, and that's not true for merge sort. It's 2n or 3n. Now I can put there 3n and do the same thing, just do a little bit more math. Because it's the first example, I want to do it simple. So, what does it mean to iterate? What does iterate brute force this recurrence means what?
n by 2,
Apply it again for
n by 2.
T of n by 2, right? So now I still have 2 what would it take to write the same recurrence, but not for n, but instead for t of n by 2? 2
n by
T of n by 4
n by 4
plus n by 2.
plus n.
plus, I still have this n at the end, right? Everybody sees that what I'm doing here. I apply the same recurrence, but not for n, for t of n by 2. Because the recurrence have to be true for any n, right? Now, I'm skipping the part where it says, well, if n is 25, 25 by 2 is 12.5, doesn't work. There is ways mathematically to prove that that's not a problem for order of growth. Remember, in here, we are not trying to figure out what is t of 25 or t of 12. What are we trying to do here? Establish the order of growth. So our job here, what we want, goal, is t of n is theta of a known function, right? A function that's explicit. So we're not going to care about exact values. We're going to care it grows like, in this case, the answer will be? What is the answer? N log n. So that's what we want to prove, not any exact value. Okay, so let's write this up. This is 4, t of n by 4, right? Plus how many n's are here if I add them up? 2n, right? Because 2 times n by 2 it's an n, plus another n, that's 2n. Right? So now I'm going to do what? Again, 4, how much is that?
2t n by 8
N by 8
plus n by 4 n by 4 plus 2n.
So again, I group the terms. What do I get? 8.
3n by 8 plus 3n. That is.
Can do it again if I want to. 8. I like to put these brackets, big brackets squared, because visually for me, you don't have to do that, just for me as a helper. It tells me what I've just done. I took that t of something, and everything, when I apply the whole formula, is inside the bracket. In this case, this is a very trivial example, but in harder problems, it makes sense to see that bracket because there's really monsters in there, okay, when these things expand. And you're going to want to know, okay, I expanded that into what? So having a way to see what you just expanded, you can use a red pen, or you can put a bracket or circle it, whatever it's easier, with visually helping you to do this. Okay? So what do I have now? 2 n by 16 plus n by 8 plus 3n. How much is this?
16
16.
t n by 16
t of n by
plus
16
4n.
plus 4n. At some point, if I use this method, brute force iteration, I have to figure out this pattern.
Yes.
Meaning, after k steps, what is this going to be equal with? Is there a way, can anybody guess a pattern? That's what happened after 4 steps, after 5 steps, 6 steps. Can anybody guess what is this going to be? K, P of n
plus kn.
Okay, this is a guess. As in, of course, in this example, it's very, very easy. All of you can guess it. But what in a complicated example? How do you guess it, right? It may take 3 steps, 5 steps, 7 steps. It may take more time, right? The point of this iteration method is to figure out, okay, at some point I can tell what the pattern is. Now, what happens after? I figure out the last k. If I have the pattern, I say how many times this is going to go. What's going to be the moment where this stops? What's going to stopping at some k? At some, assuming n is fixed, so I start with n equals say 1,000. At some point, this is going to stop. What's that point? Somebody.
And n equal to 1.
It's not gonna, n is fixed in here. See, n, I leave the same n. What changes here is the k.
Yeah.
And equals to 2 big about k.
So what's gonna stop what you want to say is that inside of t,
Yeah, that would be one.
1.
it's gonna have a stop condition to it. This part inside of t will reach a base case. So the last k, it's equivalent to say n divided by 2 to the k is approximately 1. Which means k is approximately, what k do I need so n by 2 to the k become approximately 1?
Okay.
Log base 2 of n. If k becomes log base 2 of n, the inside of t, it's n divided by n, right? Hands up who's with me on this part, specifically on how do I stop. That's not always true. What if this thing here would be n minus 2k? Then when does it stop? What k do I need to stop this thing? N by 2. The base case in that relation will be t of 0. In this, I'm going to get what base case? T of 1. So when I do the last thing, I'm going to get 2 at what power? Log base 2 of n times t of 1, because that's how I pick the k, to get t of 1 inside the t, plus what?
Log of n to the
Log of n
times n.
Log base 2 of n times n. So
This is n.
what is this?
N.
How much is 2 at
N.
log
N.
base 2 of n? That's n times t of 1. T of 1, we don't care the value, but we know it's some value. It's a constant, right?
Yes, of course.
Plus
N.
and log n.
theta of n log n. Right? I say theta because
Base.
log base 2, if I change the base, going to become a different, I multiply with a constant go out. Now, what is n log n compared to n times a constant?
Great.
Strictly greater. N log n is going to be greater. So the whole thing here is going to be theta of n log n. Okay. That's the undergraduate method for deal with recurrences. Now, this, if it's rigorous, so I'm going to talk a little bit today and more Friday about what rigorous means. But if you do it like this, if you expand a few times, then you figure out the pattern, and then you stop it, you figure out the last case. This is a complete argument. You don't need other things. Okay? So this will be a complete answer. If you do this, I tell you, give a recurrence and you do this, you solve it, you get theta of n log n, you're done. If you go to a math class, there is something else that you have to do in a math class that you don't have to do in this class. That is, once you guess the pattern, you have to do what? That we didn't do here, but you do in a math class. Prove the pattern by induction. So this would require an induction proof if you are in a math class. You still have to guess the pattern, just like we did here. But then you say, if after k steps, this is how it looks, after k plus 1 steps, it'd be 2 at k plus 1 plus blah, blah, blah. You'd have to prove that. Effectively running another iteration in k and get the same k plus 1 expression after one round. In here, you don't have to do that. Assuming you guess this correctly, we believe you. Yeah? The part with rigorosity that's going to matter, it's going to be that sometimes this is too hard to write as a pattern. It's going to be a monster expression, or maybe we can approximate a little bit. You're not going to be able to find the exact pattern. So here's another way to do this. It's not this side. I want to put that here from the very beginning, and then we're going to run some other examples. Substitution method. It's really two things. You're going to love this. First, you have to guess the answer. Now, guess is a guess. The good part about a guess is that you don't have to justify it. Right? Whatever. Right? You can copy it from your neighbor. Right? You don't have to explain how you got it. A guess, it's a guess. The bad part about it is that if you guess it wrong, you would not know it's wrong. Right? How do you know a guess is wrong? So then you have to prove it. Usually by induction. Doesn't have to be by induction. Not all the proofs are by induction, but most of them are. So how would we do this for this problem? I'm going to guess from the very beginning. So I have the relationship T of n is 2 T of n by 2 plus, say, n. Again, that's not exactly merge sort because merge sort doesn't do exactly n steps when it does the merging, but let's just say this is recurrence. I'm going to guess. The best guesses I should put here, theta if you can. So if we can guess a theta, theta is the best approximation because it bounds lower bound and upper bound, right? If I cannot do theta, what other options I have? A different lower bound, that be an omega, and the upper bound. Like say, I say, the best guess I could have here is T of n is omega of n log n, which is correct. And that tells me it's like n log n. But a not so good guess would be T of n is O of n squared, and it's omega of n. Would that be correct? N log n is O of n squared and omega of n? That's correct.
Yes.
But it's not as good as saying it's exactly n log n. If I say this could be anywhere between n and n squared.
Yes.
Because all these functions would be bigger than n, or at least that big, or n smaller than n squared. Right? But it doesn't say exactly it's n log n. How about small omega of n and small o? This is big O here. This is small o of n squared. Would that be true? This function is strictly bigger than n. The ratio between that and n is infinity. And strictly smaller than n squared. Is that true? So big O means it could be n squared. It's at most n squared. Small o means it's definitely smaller than n squared. In other words, the fraction between T of n and n squared has to converge to 0.
Yeah.
Is that true? Yes. How is this guess compared to theta of n log n? This guess in here is as good as theta of n log n? No. There's still many functions that are strictly bigger than n and strictly smaller than n squared. And I don't know it's exactly n log n, right? Because there's a few of them. N log n is the best guess because it specifies exactly, it grows like n log n. So if you can, theta is the best guess you can have. If you cannot, then this would be a better guess than this because this is more strict. It tells you it's strictly bigger than n, it's strictly smaller than n squared. While this one here says it's at least like n and at most like n squared. So suppose I have this guess. What does that mean? T of n is smaller than b n log n and bigger than c n log n, right? There exists c smaller than d and some n0 for which this happens, by definition, right? That's what this guess means, that this function T of n is smaller than that and bigger than that. Assuming I can guess the constants or I can compute the constants. I can choose the constants to anything I want. And it doesn't have to be true in the beginning. Like I said, it starts at some point, right? How do I prove this thing? I'm going to use induction. I have to make two proofs now, right? So let's proceed. Proof. The first proof is T of n is smaller than b n log n. Now again, T of n, it's a recurrence. I don't have the base like in Fibonacci. I don't have T of 0 and T of 1. I know there are some values, but I don't know which ones they are. There'll be a base case, like in induction. T of 1 has to be smaller than D times 1 times
Log.
how much is log of 1?
0.
0. Okay. How about T of 2 then? D times 2 times log of 2. Assume it's log base 2.
1.
1. So this will serve as some sort of constraints. And since I don't care about the n0, I can choose, if I don't like these base cases, I can choose a base case that's later, right? Because I can choose my n0, so I can say, okay, what's T of 3 or T of 4 maybe? More than D times 4 times log base 2 of 4? 2, right? So they don't have to all be satisfied. Because again, I can pick the n0 where I start. So maybe I start at 4. And then I have this base case. I don't need the other ones. What's the induction step? Induction step, the first thing we have to write the step down. What is it that we prove? So just by the nature of the recurrence should tell you from where to where we go in this induction. So we're going to be like, if we have this, then we prove that. But what is it that we have in induction? We have the relationship we want, but for what?
N.
I think, okay, we can write it here for n, and then move to the next. Or you can write it for the previous and move to n, whatever it's easier. For me, it's easier to move to n here. So this is what I'm going to prove. T of n is smaller than what I need, dn log base 2 of n. I'm going to choose log base 2. Again, base doesn't matter because all the logarithms I can multiply, include that multiplication in d and be done with it. So to simplicity, I use log base 2. The question is, what do I need an induction step to prove this? Normal induction, this weak induction, so to speak. By the way, weak induction only exists in the United States. In my country, we never heard of weak induction, but we call it weak induction. Will be from?
N-1.
Right? It's either from n minus 1 to n, or from n to n plus 1. But that won't work in here. That would be weak induction. But it's not going to work because of the nature of my recurrence. My recurrence is not from n minus 1 to n. My recurrence is from n by 2 to n. So that tells me what I need in my induction hypothesis.
T of n by 2.
I need the same relation for n by 2. T of n by 2 smaller than, how do I write that other term? N by 2, D, sorry.
D n by 2.
2 log of n by 2. So my induction step, my right is not working today. My induction step says, if you know this is true at the half, then you prove it for the n. Now suppose I want to from n go to somewhere else. That would be equally valid. I write this T of n is more than d n log of n implies
2n.
T of 2n is the same thing written in n or n by 2 because this is just a variable. Again, we skip in here all the issues with what if n by 2 is not an integer. We don't worry about that. Somehow, the book has a little appendix to deal with those problems. Mathematically, you can prove that by taking floors and ceilings, you can make this work. So you don't have to use floors and ceilings to say what if n by 2 is not an integer, make an integer. Don't worry about that. But we need to make this proof. So all inductions proof will start from T of n, right? And the first thing I do, I'm going to apply the recurrence. 2 of n by 2, 2d of n by 2 plus n. So now what do I do? I use the induction hypothesis on T of n by 2, right? In induction, this is the part that I can use in my proof if I'm getting to here. If I do a proof without using this, that's not a proof by induction. You may be able to do it without induction, but in an induction proof, you always have to use the induction hypothesis. Is the notion of, I already proved it for n equal 50, n by 2 equal 50. Assuming I prove the 50, now I prove 100. And then I prove 100, I'm going to prove 200. That's how all induction goes, step by step. Right? So I'm going to use that. This is d, n by 2, right? It's a 2 in the front, 2, d n by 2. Log of n by 2, right? And then plus n. Am I then doing this right? So I apply this, I say T of n by 2 is more than that, so this is plus n, right? And now what? This is n d log n by 2 plus n, right? The best thing to do once I apply the induction hypothesis, I'm giving you a friendly advice here. You can do anything you want mathematically if you're rigorous, but the best thing to do is to stop and make a plan. Right? Say, here's what I am, and where is it that I'm trying to go with this? I'm trying to get here, right? So how do I get from here to there? Some people prefer to do a few more steps and then make a plan. I mean, that's up to you. For those induction proofs, unless they are completely trivial, it's better to, once you do the initial induction application, to step for a second and say, wait a minute, how is this stuff going to work for me? And I'm looking now, there is something in here, a common factor that I have in both parts. Which one is that? I'm trying to get to here. It's not, D is not a common factor because this doesn't have a D. And I have an n times something, and this is an n times something. So the n will, whatever it is, it goes away. So then I'm left with what? D log base 2 of n, and this is D log base 2 of n by 2 plus 1. Right? So one way to, you got to make some plan. This is the moment when people take a scrap paper and try to figure out what's going on, like some calculations, maybe I can make it work. Another way, which is what I usually do, is to say here's what I want, so I put my want on this, which means I don't have it, but I want to prove it. That's d n log n. Now, that means I can divide by n the whole equation. I'm going to get what?
D log n by 2.
D log
n by 2.
I can expand this n by 2 into d of log of n minus d of log of 2, right?
Minus, yes.
Minus 1.
Plus
1.
1. It's smaller than, this is again 1. Because I didn't prove it. It's what I want to prove. I divide by n there, so it's d
log n,
right?
Yeah.
So how do I work this out? Remember, want means I don't have it, I want to prove it. But equivalent, every time you see this sign, means this is the same as that, or this is the same as that. So in other words, if I could prove the last one, all those ones before would be equivalent to it, right? So what does this mean? This is d log n minus d. This is 1, right?
Yeah.
1 times d, that's minus d.
Plus 1.
Plus 1 has to be smaller than
D log n.
d log n. So it means 1 has to be smaller than d. Right? Again, equivalent. And to be formal, I need to put 1 here. 1. For people who use scrap paper, they wouldn't write this up in the exam. They would figure out that's what they need. They will say in here, what do I do here? How do I say, okay, that I can achieve this? How can I achieve this one?
You can choose a constant.
I can
You choose a constant.
choose the proper constant, right? So I say right here, okay, done, okay, check mark, whatever you like, by choosing d equal,
Greater than or equal to.
say I choose d equal 3. Such a choice will make this true, equivalent this true, equivalent that true, so on and so forth. Now if you prefer using a scrap paper, you wouldn't write all this once. You would stop right here and say, choose d equal 3, make everything work out. To me, it makes more sense to write that because it shows the way you think, you know. If you wouldn't, sometimes in math books, they skip all this part. And right here, they tell you, choose d equal 3. And you'd be like, okay, nice, how did you get it, right? It works out, because d equal 3, you work backwards, it improves the relation, but you see that in math book sometimes says, choose that constant 4.75, you're like, okay, I have no clue how you got it here. I prefer you guys writing this once, so I know what's in your mind, okay? This is how I got there, and once I make this work, I can make the other ones work. So that proves one part, the D part. I still have the C part to prove. Right? So how do I do that? Now prove the C part, which is Cn log n, smaller than T of n. I'm going to do the same, or at least try. By the way, I'm not quite done here. The base cases impose a condition to me. Suppose I want this base case right here.
It has to be less than D.
What is this equivalent with for D? What is this base case? Suppose I want to start at 4 and 0 equal 4. This base case will mean what? D has to be bigger than D of 4
T4 divided by 8.
divided by
8.
8. And this says D has to be bigger than 1. So what D do I actually need? I need a D that is maximum between
T4
1.
by
It has to be bigger than that, and T of 4 by 8. Because I need to satisfy my concern on D here, but I also need to satisfy the base case. Now that's all formalism, because in practice we'll skip some of these details. Right? But rigorously, I would need a base case to start my induction. And 4, I just picked the n0 equal 4. We could have chosen n0 equal 10 if we wanted. Okay, how do I do the other one? I'm going to skip the base cases. You guys can figure those out. But I'm going to do the induction step. What am I trying to prove here? If T of n by 2 it's bigger than Cn by 2 log of n by 2, right? Then
T of n.
T of n is bigger than Cn log n. So how do I prove this thing? Well, I start the same like in here. T of n is 2 T of n by 2 plus n. I apply the induction hypothesis of T of n by 2, right? So that's going to be bigger than C2 C n by 2 log of n by 2 plus n. Like there, I'm going to say I want this to be bigger than Cn log n to make my proof work, right? Because if I get this done, then T of n is bigger than that. Now, what's that equivalent with? I can get rid of the n like before, divide by n. So what do I get? C log of n by 2
Plus 1.
plus 1 has to be bigger than,
C log n.
okay? This is
Um,
C log n
minus
minus
C.
C, right? Log base 2 is 2.
Plus
Minus
1.
C plus 1 has to be bigger than C log n, which is equivalent All these are ones
Less
here.
than or
One,
equal to 1.
1, 1. None of those things is proven. I want them to be true. So I need what?
C less than or equal to 1.
1 has to be bigger than C. So I can choose
1 by
here C equal 1.
1. Hmm.
But you'd have to check to see if that works for the base cases. Right? So since this part here doesn't allow me a C bigger than 1, I'm limited to C1 or smaller.
Hmm.
I pick 1, but then I'd have to adjust N0. I can choose the N0. So that would be my best case. What do I need if I choose C equal 1? For N0 to happen. What would this look for N0 and C equal 1? I need N0 times log of N0 to be smaller than T of N0. So, not sure this is always, I mean, you'd have to see why this is possible, right? C equal 1 would work here. But what if I cannot find such a 0? How do I deal with this? Can I choose a different C?
Yeah, I mean, yeah.
I can choose a C, say, half. Will that make my life easier here? What would I need? So any C lower than 1 will allow this to happen. Right? Because I did it by equivalence. As long as C is more than 1, I don't have to worry about this. What would this be here?
Less than equal to 2t and
That'll be 1/2, right?
Yes.
Certainly makes my life easier. So that's good, because I can say, okay, pick the N0 that you want, say 10. Then T of 10 is some value, right? So if I choose N0 equal 10, I get what? T of 10 has to be bigger than C times 10 times log of 10. That means C has to be smaller than T of 10 divided by 10 times log of 10, right? And now I can pick a C that's smaller than this and smaller than 1, but bigger than 0. All these constants have to be bigger than 0. It shows that I can make such a C work. So we call this substitution method or the guess method. So what happened here? I made a guess, then I proved the guess by induction. Now, in practice, for hard problems, for easy problems, we're going to have this master theorem and some other ways to think about it. But for hard problems, you might need to do a combination of those two things. Meaning, run iteration, get to some sort of pattern. If you can rigorously write that pattern down and work it out, do that. But in most cases, if the problem's hard, we won't be able to. We won't be able to rigorously run the pattern down and deal with it. But what we could do in here, instead of writing the pattern down, do what? Make a guess. We say, I don't know the pattern exact, but I can guess this is like n cubed. Looks to me like n cubed. And then try to make an induction proof. Okay? Again, if you do this correctly here rigorously, you can just run it down and get the answer, and that's fine. But if you cannot, then you need to make another proof. Let me try one more. See if I can get it done. Maybe you guys need to finish it at home. May take 2 minutes extra, but how about I do the iteration and you take it home and you do, or look at the slides and do the induction proof. T of n is 4T of n by 2 plus n. I'm going to do the iteration method. This iteration has to do with the trees that somebody mentioned. I can write the iteration method instead of this brute force as trees that are visually expanding. It's the same thing, just written with trees instead of algebra. I'm going to brute force this, so what is equal with? 4 square bracket. How do I apply it in here? So how much is this?
N by 2, 3n by 2.
How much?
3n by 2. 3n by 2.
By 3 and by 2.
3n, right?
3n, sorry.
Okay, again. So 16, what is that? By 8, right?
By 8 and by 4.
3n. So how much is the thing in the coefficient? 64.
N by 8 plus 5n.
16.
No, 5.
7.
Okay. Again.
Two 56 into n by 16 plus 15n.
Okay. Let's see. Can I write the general pattern?
4 to the power k.
How much is the k in here?
2 raised to
If I say 4 to the k, what's the k in here? 4. What is this n by 16? N by what?
2k.
2 to the k, right?
Yeah.
Right, because for 4, this is the k4, this is k3, that's 2 to the 3, right? Hands up who's with me here. Okay. And who's this 15, 7, so on and so forth?
2k minus 1.
What?
No, no, no.
One person.
2 to the k minus 1.
One person. Hands up first. Yes.
2 raised to power k minus 1 into n.
2 raised to the power k minus 1 and
Yes.
like that.
Right.
So that's 2 to the 4. Okay. So if that is correct, what's the last k? When this thing stops?
Then n is equal
When
to
in the inside it's 1 like before. So I need n by 2 to the k to be about 1, which means k has to be about log base 2 of n.
Right.
So this would look like what?
4 raised to
4 to the
log of n to the base 2.
log base 2 of n. T of 1, right?
Plus
Log base 2
2
of n.
raised to
Plus 2 at what power?
log of n to the base 2 minus 1
Base 2 of n minus 1 down, right?
into n.
Okay. So how much is 4 at base log base 2 of n?
2n squared. n squared.
2n squared.
n square.
Okay. So 4 at the power log base 2 of n is, this is 2 at 2, right? Log base 2 of n. I swap them, 2 at log base 2 of n, it's n squared. Yeah? Make sure you're familiar with this kind of manipulations. So this is n squared
T of 1
times t of 1
plus n.
plus,
N minus.
this is what? N minus 1 times n?
Times n.
It's n squared minus n, right?
Yes.
What's the order of this?
N squared.
n squared.
I could do this because this is n squared, that's n squared, the lower term doesn't matter, right? Every n squared polynomial will be n squared, that's the answer. This is a correct, complete answer because I could do the pattern and argue it and come up with an answer. Now, if I could not, if I could guess around here, say I don't know the pattern, but I could guess it's n squared somehow, I could make the proofs by induction with n squared. So try this by next time, make those proofs by induction, both for C and D. One of them will not work. Just, I mean, you can still do it, but you need a trick. So when you say smaller than D n squared and bigger than C n squared, the typical way to move forward will fail on one of the proofs. And you can still do it. There is a trick in the notes for how to do that by induction. So you can take a look at that. And I won't get back to this example. I'll do other things. But I could get back to it at office hours if we need to. Office hours will probably happen Wednesday with me and the TAs, Mondays with just me in the evening, and Friday with just the TAs. So they will answer questions about grading mostly, and I'll answer conceptual questions about the class. Everybody got a share with the Dropbox?
Yes.
How many people shared that Dropbox? Okay, so we need you to create that folder like it says in the things, and there is an email address, a Dropbox ID to share with. That's where the TAs will see your submissions, and that's where they're going to grade it. They're going to take your PDFs and mark them with what's wrong and what's right in there, okay? So we're not going to submit anything on paper. Can you press the record button? It's on the, actually he can do it easier. It's on your side. There's a red button on the camera. Yeah, right.